everyone. Now I am going to explain you about analysis of a parallel RLC circuit. Okay, consider this parallel RLC circuit. Here the current source is given. Here the switch is given. So this symbol indicates that the switch is going to open at t is equal to 0 condition. So apply at t is equal to 0 condition. The switch is going to open and the current source is connected to this parallel RLC circuit. So this is the equivalent circuit diagram. Okay, the current source I is connected to this parallel RLC circuit, and then also we know the parallel combination of LNC circuit is nothing but a tank circuit. So here for the analysis of this parallel RLC, I am going to apply a KCL analysis. So for node A, so here the KCL analysis means what is the current entering to a node that should be equal to the leaving currents. So here the current should be equal to the current across your resistor, inductor, capacitor. So first of all we just write down this current across a resistor is nothing but V by R, across the inductor is nothing but 1 by L integral V dt, across the capacitor is nothing but C into dV by dt. So therefore by applying a KCL to node A, we are getting a current I equal to current across a resistor, inductor, capacitor. So we know I is equal to across a resistor is nothing but V by R, inductor is nothing but 1 by L integral V dt, across a capacitor is nothing but C into dV by dt. So make it as equation number 2. So here we are getting an integral term as well as differential term. Just apply the differentiation to this equation with respect to the t. So by applying a differentiation, the differentiation of this constant is nothing but 0. So di by dt, which is equal to 1 by R into dV by dt, okay, plus 1 by L into integral differentiation will get cancelled. So you will get 1 by L into V plus again here for this one C into d square V by dt square. Okay. So by solving this we are getting a equation C into d square V by dt square plus 1 by L into V into plus 1 by R into dV by dt. So again to form a second order differential equation, I am taking this C as a outside. So I am getting a equation d square V by dt square plus 1 by RC into dV by dt plus 1 by LC V is equal to 0. So this is nothing but the equation d square plus 1 by RC of d plus 1 by LC into V, which is equal to 0. So now this equation looks like a characteristic equation ax square plus bx plus c. So in this one just assume a is equal to 1, b is equal to 1 by RC, c is equal to 1 by LC. Then the roots are nothing but minus b plus or minus b square minus 4ac by 2a. Just to simply substitute that roots. So for this differential equation, so we are getting a 2 roots d1 which is equal to minus b. So b is nothing but minus 1 by RC plus under root of b square. No? So minus 1 by RC whole square, nothing but 1 by RC whole square minus 4 into a value is 1, c value is 1 by LC by 2a. So therefore the root d1 is equal to, so I am making this denominator term to here. So it will become minus 1 by 2 RC plus again this term I am sending it to a square root term. It will become square. So therefore I am getting a term 1 by RC whole square into 4. So I am writing this 4 value inside this, means you will get a 1 by 2 RC whole square minus 4 into 1 by LC by 4. Nothing but 4 will get cancelled. You will get a value of LC. So here again we are getting a roots of two terms. One is minus 1 by 2 RC plus again one square root term. So I am taking this as a minus 1 by 2 RC as K1. This entire term as a K2. So similarly the second root D2 is equal to minus B. Again minus 1 by 2 RC whole square minus 1 by LC under root. So which is nothing but K1 minus K2. So from that I am writing K1 is equal to minus 1 by 2 RC. K2 is nothing but plus or minus under root of 1 by 2 RC whole square minus 1 by LC square. Therefore the total roots are like d1 minus of k1 plus k2, again d2 minus of k1 minus k2, which is equal to 0. So this is d2. Okay, so just assume to find out if k2 value is real, if k2 is imaginary. If k2 is 0, we'll get three different types of responses. Okay, just assume if k2 is real. So when k2 is real, if this under root term 1 by 2 RC whole square is, which is much greater than the second term, then only you will get a k2 value as real value. Therefore, so if k2 is real when 1 by 2 RC whole square is much greater than 1 by LC, so means if this value is much more greater than 1 by LC term, you will get a positive real values. So therefore the roots are real and it may be negative. Why? Because here we are getting a k2 value as real values. Okay, so here k1 is minus 1 by 2 RC, k2 is real value, means you will get a real and negative values, because you are k1 plus k2 here, k1 minus k2, you will get a real and negative values. So therefore the solution is nothing but c1 into e power of minus k1 first root, means this is the one differential equation. When the for this differential equation we have the roots, the solution is nothing but I1 is equal to k1 into e power minus pt. So just assume this is like p1 p. So therefore the solution is nothing but, instead of k1 there, here we are writing it from c1 into e power minus pt is nothing but k1 plus k2. Similarly, so for this one, c2 into e power of k1 minus k2 into t, means we will get a over damped response. Similarly for case 2, just assume if k2 is imaginary when this 1 by 2 RC is much less than 1 by LC term. So therefore the roots are complex conjugates. So the roots are unequal and this is the roots d1 minus of. So we are getting imaginary roots now. So therefore k1 plus jk2, again k1 minus jk2, and the solution is nothing but, so here in this both term k1 is real value. So the solution is e power minus k1t into, and these are the imaginary values. So you will get a complex conjugate nothing but, so from this one, this is c1 into cos k2t plus c2 sin k2t. Will get a underdamped response. Similarly for K3 also. So in the third case, just assume K2 is 0, means 1 by 2 RC whole square is equal to 1 by LC. So you will get these two terms are real and equal. Means if these two terms are equal, means you will get K2 is 0. So then you have only the one term K1 value only. So therefore this is the roots are real and equal. You will get d1 minus k1 into d2 minus k1. So therefore the overall solution is nothing but v into e power minus k1t into c1 plus c2 of t volts. So we'll get a critically damped case. Okay, and here one more case. Just assume if k1 is 0, nothing but 1 by 2 RC whole term is 0, means you will get a imaginary roots and you will get a solution v1 of t. V of t is equal to c1 cos omega t plus c2 sin omega t.